Okay, so in this video, we're going to start talking about nuclear power. And some of nuclear power we've already talked about, so some of these concepts we're going to go through kind of quickly. Um, but basically, nuclear power as of 2010 represented about 6% of primary energy use in the world. And some countries use a lot of nuclear power, like France, I know I think north of 70% of their energy or of their electricity comes from nuclear, whereas our numbers is somewhere in the 10 to 20% range. But there's not a lot of countries that have access to nuclear technology, and so overall across the world it represents a relatively low percentage of primary energy source. When we talk about nuclear power in the current state in the world, what we're talking about is energy generated through nuclear fission, and using the heat from fission to operate a thermal power station. We've talked about how thermal power stations work in past videos, where basically you take some type of heat source and use it to heat water and produce steam, and the steam drives a turbine, etc., etc. Um, and so these fission plants use fissile materials like uranium or plutonium as a nuclear fuel source. Now, what we currently don't have when we talk about nuclear power is fusion power plants. And this is really would be the ideal energy source because when you talk about fusion power, um, the fuel for fusion is hydrogen essentially, and there is a lot of hydrogen in the ocean because water is H2O. And so with fusion, we have an abundance of fuel. In a normal fusion reaction, we produce a lot of energy, but we don't really produce any radioactive waste, and so there's a small amount of pollutants as compared to like fission. And of course, enormous energy production. Think fusion is what powers the sun. Okay, and so the sun generates its enormous energy from nuclear fusion. And so even though we have accomplished fusion on Earth. If you've ever heard of the H bomb, that's a fusion bomb. Um, we haven't developed our technology to the point where we can use nuclear fusion as a viable means of producing electricity where we get more energy out than we put in. And so currently there's no commercial fusion plants in existence. Okay, so currently all nuclear power is generated through nuclear fission, and so when you talk about nuclear power, most of the time you're talking about fission. Okay, but of course the goal is fusion. I'm going to link a video that I want you to watch telling you about nuclear fusion, even though that's not currently a energy source that we have in use. This is something that has been in the works for decades. There's a lot of money that's been invested in figuring out nuclear fusion, and really, that's the solution to the world's energy crisis. And whoever solves that is probably going to win a Nobel Prize, or at least become very rich for sure. And so, even though we don't currently have nuclear fusion power plants now, it would be good to know what exactly that is just for the future. All right, so just to kind of recap what fission is, when we talk about nuclear fission, we're basically talking about splitting a very heavy, unstable nucleus into two smaller daughter nuclei. And the way we accomplish this splitting is essentially by hitting a large nucleus, an unstable nucleus, with a neutron. And so what you can see here on your screen is an example of a possible fission reaction. And so what's happening is on the far left, you can see a neutron is being absorbed by, this is uranium-235, which is a fissile isotope of uranium, momentarily becoming uranium-236, which is highly, highly unstable, and then splitting into two smaller daughter nuclei, in this case, xeon-140 and strontium-94, plus, and this is the key element, plus additional neutrons. And so in nuclear fission, you always have two or sometimes three neutrons produced as a result of the reaction, not to mention an enormous amount of energy, because there's a mass defect in this equation. There's more mass on the left side of the equation than there is on the right side of the equation. So some of that mass is converted into energy because, E equals mc squared and mass energy equivalence and all that stuff. Okay, so that's basically the principle behind nuclear fission. Now, the key element to fission is the neutrons that are produced under certain circumstances can be used to create additional fission reactions. And of course, I'm highly oversimplifying because actually getting that to happen is very difficult. But under the right circumstances, these daughter neutrons, in this reaction, it's two neutrons, but there's other fission reactions with different isotopes that are fissile that can produce, more than 2 neutrons, like 3 neutrons. The idea is if those neutrons go on to cause additional fission reactions, you can get what's called a chain reaction. Okay, and so you can arrange this chain reaction so that if you want to, it can grow exponentially. Um, in the case of an exponential growth chain reaction, you actually don't want that in a nuclear power plant. This whole exponential growth. When I say exponential growth, what I mean is, you get one fission reaction, and then those 2 neutrons hit 2 other nuclei, right, and cause 2 fissions, and then those 2 fissions produce 4 neutrons, and so that's what I mean by exponential growth. Okay, with each reaction releasing more and more energy. So this type of exponential growth scenario is what's called an uncontrolled chain reaction, and you don't want that in a nuclear power plant. What you would use that for is a nuclear bomb. Okay, and so nuclear bomb uses this uncontrolled exponential growth chain reaction. You want what's called a controlled chain reaction in a nuclear power plant, where basically you don't want it to exponentially grow. Basically, you want on average one of those neutrons to produce another fission reaction so that you get a steady stream of energy produced, but it doesn't like grow out of control. And again, I'm highly simplifying how that works. Actually getting it to come out that way is not so easy, um, but we might talk more about that later. Okay, and so here you can kind of see a diagram showing you how a nuclear power station works. Um, for the most part, it's the same as a fossil fuel power station, aside from what it is that produces the heat. Okay, you're still using heat and using the heat to boil water, create steam, etc., turn a turbine, generator, all that stuff. The only difference is now the heat, rather than coming from combustion of coal or combustion of natural gas, is the fission of uranium. And so those that reactor core has a bunch of these what's called fuel rods, and these fuel rods have these pellets that contain I want to say it's uranium oxide, and so those are all stacked inside the core, and then the core can be bombarded with neutrons to produce the fission reaction. So the whole thing gets really, really hot um, and produces that heat that we talked about. Just to show you some examples of what some IB questions might look like as far as nuclear goes. And this is kind of a review because most of these concepts we've talked about so far in past units. Okay, so here, state the name given to this type of nuclear reaction. This is obviously a fission reaction. This is not the same fission reaction we saw before, but because the daughter nuclei are not the same. Energy is liberated in this reaction. In what form does this energy appear? It appears in the form of kinetic energy of these products. And so the barium, so when we say energy is released, what we really mean is, the barium, the krypton, and the neutrons have a lot of energy, and then they can collide with other things and transfer their energy that way. So when we say energy is released in a reaction, what we really mean is the products not only have their own mass energy, but they also have kinetic energy. Then they can like run into stuff and transfer the energy that way. Okay, so heat and some kinetic energy of the product neutrons. All right, so it turns out that natural uranium that you can just mine, the vast majority of it, more than 99% of it, is an isotope called uranium-238. And the thing about uranium-238 is it's not what's called fissile, meaning it does not easily undergo fission. Okay, the isotope that is fissile is uranium-235, but only about 0.7% of natural uranium is the 235 isotope. Okay, whereas, more than 99% of natural uranium is 238. So you can't just pick up a piece of uranium off the ground and stick it in a bomb, right? That's not that easy. Okay, what you need to do is you need to take that uranium and carry it through a process that's called enrichment. And enrichment is basically a process whereby you somehow increase the percentage of fissile material in a substance, meaning you take your sample, your hunk of uranium rock that's 99% of uranium, and you undergo some process so that at the end of the process you have less than 99% of 238 and a higher percentage of 235. Now, just to be very, very clear, so you don't say the wrong thing answering some questions, you cannot turn uranium-235 into 238. That's not physically possible. That's not how that works. Okay, when we talk about enrichment, we are not talking about turning 235 into 238. All right, just to be clear. When we talk about uranium enrichment, really what we're talking about is taking a sample, separating out the 238, removing some of the 238, and if you take away the 238 atoms, then what you're left over has a higher percentage of the 235 isotope. And if you keep undergoing that process, eventually that 0.7% can increase. To use in a nuclear power plant, you need it somewhere around like 3 to 5% rather than 0.7%. If you want to make a nuclear weapon out of it, you have to have what's called weapons grade uranium, which is more like 85% uranium-235, which is very difficult to achieve because the process I just described is quite complicated. Basically, the way it works, and again, I'm highly oversimplifying this just for the sake of time. Um, but one way this works is a process called gaseous diffusion, where basically they take the uranium, they combine it with fluorine gas, they produce a gas called uranium hexafluoride, and they essentially um, separated out based off of mass. In the past, they also did a process called centrifuging, which essentially means that you spin the gas around really fast, and then because of centripetal force, the heavier particles go to the outside of the chamber, and they can be separated out that way. Because the 238 isotope is, heavier than 235, because, well, 238's a bigger number than 235, so it's heavier. But anyway, all that to say, actually taking uranium from the ground and getting it to a point where you can do stuff with it is extremely, extremely complicated, as you can see from this diagram. All right, now here you can kind of see this is from 2007, so this is a little outdated, but this is the nuclear share of total electricity generation. And if you look, you can see, 19% of the electricity in the US in 2007 was produced by nuclear power, as opposed to in France, where it was like 77%. And so other countries, European countries, tend to be much more trusting of nuclear technology than we are. And you can debate whether or not that's a good thing or a bad thing. But there are, of course, advantages to nuclear power. I'm going to skip some of this. And we'll talk more about the advantages here in a couple minutes. Now, let's talk more about the chain reaction. So I said before how in a nuclear power plant you want a controlled nuclear reaction. That's like a technical term, so that's a word you should know. Controlled chain reaction is a chain reaction where you're only producing new fission reactions at like a 1-to-1 ratio. So, one of those two neutrons comes out and causes another fission reaction, as opposed to that uncontrolled nuclear reaction that you would have in a bomb that has that exponential growth. Okay, so we've already talked about that before. Let's see, already talked about this. There's a key fact, though, that I haven't mentioned as far as causing fission, and that's this sense right here. Neutrons have to be traveling, missed a word, be traveling relatively slowly to be captured by a uranium-235 atom. Okay, so it's way more complicated than I've actually made it sound. So the neutrons that come out of fission, the product neutrons that come out of fission, cannot like immediately cause more fission. Okay, they have to be slowed down because the neutrons released in fission, remember, have all that kinetic energy. They're moving really fast. They have to be slowed down before they can actually cause more fission by hitting another 235 nucleus. Okay. In other words, most of the neutrons produced in a reactor are what's called fast neutrons, which are not likely to cause nuclear fission. All right, so we have to use what's called a moderator to slow down the fast neutrons, and if we slow them down enough, then they'll have just the right energy to continue the fission process. Okay, and when I say we use moderators, basically what I mean is we take those fuel rods that I mentioned before, and we basically surround them with some type of material. And the idea is that the neutrons are going to come out, collide with the atoms of the moderator, and when they collide, they're going to transfer their energy to the moderator, and that's going to slow them down. And so we can use different materials as moderators. Some countries use graphite. Some countries use what's called light water, which is just like normal water. Some countries use what's called heavy water. Heavy water, well, water is H2O. Okay, normally when you talk about hydrogen, you talk about like H1. Okay, but there's different isotopes of hydrogen like H2, which is called deuterium, and H3, which is called tritium. And so when you talk about like normal water that you drink like on a day-to-day basis, that H2O is made with this type of hydrogen. Heavy water is still H2O, but the H is this type of hydrogen, H2, deuterium. Okay, and so that's why it's called heavy water. And so again, the idea is that you just like surround the fuel rods with this like material, and the neutrons that are released in fission will, collide and transfer their energy and slow down, and then eventually those neutrons will be slow enough that they can cause additional fission reactions, and so you can keep getting that chain reaction. I believe in this country, I think in the US we use uh, just normal light water. Um, I know other countries use different types of moderators though. All right, so here is a question to ask you. And we probably already talked about this, so you might be familiar with this concept. Um, Moderators are used to slow the released neutrons down to speeds where they are able to easily cause fission to occur. These neutrons are called thermal neutrons. Okay, the neutrons that are slow enough to cause fission are called thermal neutrons. If the moderator inside the reactor was suddenly removed, what would happen? Based off what we've been talking about, what do you think would happen if the moderator inside the reactor was suddenly removed? And just to make this concrete, let me give you an example. Let's say we use water in this country, and let's say there's water in the core surrounding the fuel rods, and let's say the reaction all of a sudden goes out of control, right? And the water gets so hot it boils away, it evaporates, right? So the moderator is gone. What would happen to the um, nuclear reactions happening inside the core? Okay, well, hopefully you said that the reactions would stop, because remember, if you take away the moderator, those neutrons released in fission are moving too fast to cause more fission events. And so if the moderator was suddenly removed, the reactions would just stop. Okay, and so in a way, if you use water as a moderator, it's almost like a built-in safety mechanism where like if something is wrong and the water like, boils away, then it kind of shuts itself off, if that makes sense. Okay, so using water as a moderator has that like built-in advantage. Right, and the last couple elements we're going to talk about before ending this video. So we talked about fuel rods, we've talked about the moderator. Another element that you might see in a nuclear power plant is what's called control rods. Okay, and so control rods, there's a lot going on inside the core of a nuclear reactor. You got the fuel rods surrounded by the moderator, but also surrounded by what's called control rods. And control rods are made of materials that are neutron absorbent. Now, why would you want to absorb neutrons? So you might want to absorb neutrons because if you have too many neutrons, then rather than having a controlled chain reaction, you might have an uncontrolled chain reaction. So it's a very delicate balance inside a nuclear reactor. You don't want the reaction to go too fast, but you also don't want it to go too slow. And so just to give them an extra means of control, we have what's called control rods. And so the control rods can be inserted or removed from the core to change the rate of reaction, right? If you want to slow down the reaction, then you just stick the control rods all the way into the core, and it's going to suck up all the neutrons, and the reaction's just going to stop. Because without the neutrons, you can't have a chain reaction. If you want to speed up the reaction inside the core, you would remove the control rods, and then you would have more neutrons, and then you could have a faster reaction. And so one of the tasks inside the nuclear cores is like controlling the rods going in and out of the core at all times. These control rods are usually made out of cadmium or boron steel, and what happens when neutrons hit them is that they just get absorbed. Okay, so this diagram is just kind of showing you the difference between moderator and control rods. And the very last element I want to talk about is what's called the heat exchanger. Wait, where is it? Oh, here it is, the heat exchanger. So basically, when we talk about the heat exchanger, we're basically just talking about like a boiler. We're talking about the thing that has like the water that's going to, heat up and turn the steam, and the steam is going to turn the turbine and all that stuff. Okay, so when you're talking about like a heat exchanger, if you ever see that term in a question, that's basically what that is referring to. Okay, so you can see it here in the diagram where the heat exchanger is. Okay, so this is the core right here. This is where the heat takes place. The heat is transferred through water to the heat exchanger. This is where the water boils, creates steam, etc., etc. Okay, so I've very kind of quickly outlined how a nuclear power station works. We're going to go ahead and stop it there, and then in the next video we'll finish talking about nuclear power just a little bit before we move on to renewable energy. All right, so I know that was fast, as I would highly encourage you to read in your textbook about nuclear power, topic 8, because your textbook is going to be a great resource for this unit. As always, please let me know if you have any questions, and I'll see you guys in the next video.